Hey, time for your life's math and history, and we are going to take a look at a triangle prism problem. So, recently in the past few videos, we have been taking a look at light waves, and we've been also talking about their refraction, where the speed changes of light when it's crossed from one medium to another medium. We also understood Snell's law, which could help us understand at what angle is the light refracting from the normal line, meaning what is the angle the light is going through that medium when it, pretty much goes through that medium. So here is the triangle problem. There will be some things that we'll have to do, like some logical reasoning, but it will make a lot of sense why. So, a ray of green light, which is a wavelength of 542 nanometers, is in a vacuum, enters a prism shown below at an angle of 78 degrees to the surface. The index of refraction to this wavelength is 1.62 in the prism. The prism is surrounded by air. So there are 5 things we gotta do. But we can split the entire thing into two, because there's one which is E, and the other one is basically a sequence of answers. Let's try to understand E first, because that will help us clearly understand why this works. So E, find the wavelength of the green light in this prism. Remember, C equals wavelength times frequency, and the frequency is a constant. C is the symbol we use for the speed of light. So here's what we're trying to do for number E. The prism shown right over here is in the air. But we also talk about how the ray of green light is in a vacuum. So what we're trying to do is find the wavelength of the green light in nanometers. At first, when you think of wavelength, you think of this formula right over here. Velocity equals wavelength times the frequency. Okay, that will help us, but there will lead to some problems along the way that we have to solve. So let's say 3 times 10 to the power of 8, because that is the speed of light, and that's going to equal the wavelength proposed is 542 nanometers. So we are going to do parentheses 542, 542 instead, times 10 to the negative 9. Because that is going to convert from meters to nanometers. We're going to say 542 times 10 to the negative 9 in nanometers. Then we have to multiply by the frequency. When we try to solve it out, we are going to divide this side by 542 times 10 to the negative 9th, and divide this side by 542 times 10 to the negative 9th. Let's try to do that on a calculator. So when you do on a calculator, I'm just going to round to the nearest decimals. 5.53 times 10 to the 14th power. And that's going to be in hertz. That is the frequency of what is shown above right up here. We have the frequency, but we still need to find 2 more things. How fast is the light going inside that prism right over here? And number 2, what is the wavelength that is in the prism? The problem does give us the wavelength for the prism in the air. But since the triangle prism is a different medium, we have no clue what happens next. So here's what we try to do. How are we supposed to know the velocity of the light inside the prism and also the wavelength inside the prism as well? Then what we can do is multiply by the frequency of 5.53 times 10 to the 14th power. All we have is the frequency. We're missing 2 items. What can we do about that? Well, if the overall goal for the section E problem was to find the wavelength inside the prism, we have to find that. But what we could do is use another formula. That formula is going to be the index inside the prism is going to be equal to the speed of light represented as the letter C. Divide that by the velocity inside that prism. We should also add a letter P on the bottom of M to help us understand the index inside the prism. Going back to the problem right over here, the index of refraction for this wavelength is 1.62 in the prism. So we are going to add 1.62 right over here. Then we are going to have to equal that by 3 times 10 to the power of 8, because that is the speed of light. But then we have to do VP, the velocity inside that prism. So VP cancel each other out. You have to put VP as a variable right here. So 1.62 VP equals 3 times 10 to the 8th power. I just rearranged it because normally I love it and it's satisfying when you put the variable right behind the number. Divide by the 1.62 and divide by 1.62. I'm going to add a second piece of paper because it's going to help us a lot. Our velocity inside that prism should be equal to 18.5 times 10 to the negative 9. That is going to be in meters per second. But that's meters per second. We're not done yet. We got the VP, the velocity inside the prism. We can now solve to get the wavelength inside the prism. So, if VP equals the wavelength inside the prism times the frequency, we can say 18.5 times 10 to the negative 9, and that's going to equal, I'm going to put that crazy symbol right behind the frequency, so it's kind of like a variable itself. 5.53 times 10 to the power of 14. Then I'm going to put this crazy symbol right over here. And to not get confused as a number, I'm just going to put a line under it so I don't forget of it later. Now, solve. We solve by getting the wavelength inside the prism alone. Divide this side by 5.53 times 10 to the 14th power, and divide this by 5.53 times 10 to the 14th power. There's a lot of power. Power this, power that, power everywhere. When you do that, your final wavelength inside P should be equal to 3.345 times 10 to the negative 23 meters? That is very small, but we want nanometers, not just meters. So we are going to have to multiply that by 10 to the 9th. Now, when you do that, your new wavelength in the prism in nanometers is going to be 3.345 times 10 to the negative 14th nanometers. That is going to be the wavelength inside the prism for the green light. So yeah, we have done that. Oh yeah, we did use a calculator to solve it out. Well, you kind of had to use a calculator. I think that was probably the hardest part because everything else is going to be visual, and we're going to actually use that triangle right over here to help us solve the problem out. Not only that, what we did is we made another triangle right over here. So, if we make any mistakes, we could just erase them and restart. So we found the wavelength of the green light in this prism. So we're done with E. Now, what we have to try and do is find the ray in the next interference in the prism, determine the angle of refraction inside the first interface, and determine the angle of refraction in the second interface. So let's see what we can do. So we have 78 degrees going green light in that direction.